Hey kids, today we're going to talk about tolerances. A tolerance is a variation when you're building something and how far off a part is. So when you're manufacturing some sort of an item, you can't always manufacture it exactly the same. And you guys have seen this in when we were using dial calipers and those kinds of things, that parts would typically be off by a thousandths or a few thousandths. No two manufactured parts are identical, and there has to be some degree of variance in that size. Tolerances are used in production drawings to control the manufacturing process and to control a variation between the copies of the same part. In particular, tolerances are applied to mating parts in an assembly so that you make sure that one's not a little bit bigger and it won't fit then in the hole that it's supposed to fit in. So the parts that are interchangeable. Large tolerances may affect the functionality of parts. So like having something be able to be too big or too small, it might make them either like sloppy so that it's like too loose of a fit. If you're talking about two pieces that are supposed to like snap fit together. Small tolerances will affect the cost of the part. So having the ability to make a tolerance that's really small, it means that you're going to have to go through and manufacture more of them to maintain that preciseness of it. And so for a manufacturer who's going to build these things, if it's a really small tolerance, they're trying to build that thing very precise, and so they're going to, chances are, have more scrap material, and so the costs to actually produce that, thinking of like aerospace, those kinds of things, where even a thousandth of an inch makes a difference in vibration. If you're talking like building airplane parts and those kinds of things, their parts have to be off, or can't be off, more than a thousandth of an inch because it will create vibration, and then it'll eventually cause fatigue and parts to break. So the manufacturing cost for certain parts to have them that precise ends up being really extreme because of the quantity of that manufacturer ending up scrapping parts because they don't meet the tolerances or the design specifications. It will require quality control inspection. So a quality control person would be hired at a manufacturing company, and that person's job is to measure and inspect to make sure that the part is built within the specs to be able to actually be able to be put together, and that it's not out of size. And then one of the key things about remembering for engineering is don't specify a tolerance that is smaller than is necessary. All right, so there's different types of tolerances, ANSI, and then so American National Standards Institute, and ASME, American Standards for Mechanical Engineering. Each dimension shall have a tolerance except those dimensions specifically identified as reference, maximum, minimum, or stock. The tolerance may be applied directly to the dimension or indicated by a general note located in the title block. All right, so tolerances is an acceptable amount of dimensional variation. So how far off can it be built and still function correctly? All right, so there's three different basic types of tolerances that are most used on working drawings. So we've got limit dimensions, which is like it can be, for this example, 0.980 to 0.975. So you can't have a number that would be, like it couldn't be 0.981. That would be too big. Or 0.974. It wouldn't work. It has to be a number at that, equal to, or within that range. So that's a limit dimension. You're going to want to write the notes down for this because you're going to need them for the assignment sheet. So limit dimension. A bilateral dimension uses that plus or minus symbol. So in the upper right there, it's giving us the nominal dimensional, and nominal means like ideally this is the size that I want it to be. And then it gives us a plus or a plus minus symbol of greater than that or subtracting from that. So for the 1.170, it can be 1.72, or it can be 1.175. 0.68. So it can be plus or minus on that number. So bilateral, going in 2 directions. And then it can be unilateral. So uni meaning 1, and it can go, for this example, it lists the specific plus and minus. It means it can't be any smaller than that because there's probably a part that fits in there, but it can be a little bit bigger. All right, so another example of a limit dimension, it's listing the maximum and the minimum size that notch or the keyway could be. So they provide the upper and the lower limit for this dimension. Any size between or equal to the upper limit and or the lower limit is allowed. The upper limit dimension is 0.126 and the lower limit is 0.125. So they only have 1/1000th of an inch difference on that part. A bilateral is the plus or minus symbol, and the variation can be plus or minus 0.003. For the bottom dimension, the 1.5, they have plus or minus 0.05. So notice it's the hundredths place. Using the right syntax, so saying plus or minus 0.003, and being able to read it that way is something that you should practice. Or for the 1.5, plus or minus 0.05. So being able to read it in a proper way. Instead of saying plus or minus 0.05, it's not necessarily the best way to say that. If you're going to speak with someone that's manufacturing your part, you're going to say, this dimension's plus or minus 0.05. Right? Unilateral means going in one direction, and so they're going to list one of them as a 0, meaning that it has to be either this size or greater or smaller. And so they actually are able to list like in one direction, so that you may have a piece that's fitting in there, so it definitely can't be smaller or something like that. For the assignment, you're going to work to identify the different types. So like this is a practice activity, so which one is the limit dimension? And which one's bilateral? And which one's unilateral? And so they go through and they label them for you guys so that you can check to make sure you have an understanding of them. It's pretty simple to do tolerances, but what the tricky part is when you become an engineer is figuring out how much difference in part sizes do you need in order to get something to fit. Unfortunately, because of the online learning, we didn't get a chance to experience some of that. You guys would have had that same kind of experience in building your automatas and having that preciseness matter. A specific dimension means that it's the target dimension for the limits are calculated from. The limits are maximum minimum shown by the tolerance dimension. The upper limit is the maximum allowable dimension. And so you would calculate these out. So calculating out for these limit or unilateral dimension or tolerance, that upper limit specified dimension plus the positive variance, so it's 1.55 because it's the ideal 1.5 plus the 0.05, so you end up with this 1.55, and then the lower limit you would subtract it, and so you get 1.45. So you end up with a range then. So my part can actually have a dimension range between 1.55 and 1.45 for that specific measurement. The tolerance total, so the total variance, if they're asking you for the tolerance between, is actually subtracting the upper limit minus the lower limit. So the tolerance is 0.1. So that's almost 1/8 of an inch. 0.1 of an inch. Calculating tolerance again, so upper limit and lower limit for that unilateral measure. So if someone asks you what's the tolerance, you could specify 0.01. It's actually 0.1. So that's not right. It's supposed to be 0.1, you guys. General tolerances are something that are used on drawings that you don't want to list a tolerance for every single one. And so they can, like maybe the size doesn't matter. You know, if the box has to be 3 by 5 by 1, maybe the outside of the box doesn't have a specific size that, you know, if it's off by a little bit, it's okay. So what they have is these general tolerances. So they'll put this little box in the corner of their drawing sheet. So maybe just above that title block or somewhere in the corner. And what this means is any dimension that I specify that is listed to the 10th place would be plus or minus 2/100ths. Any dimension that I list the dimension to the 100th place, then it's plus or minus 100th. And then any dimension that I list 3 decimal places for would be plus or minus 5/1000ths. If it lists an angle, it'd be 1/2 degree, being able to be off by. And so this is a way to not have to list dimension or tolerances on every single dimension that you put on a drawing, but it allows your part to have some sort of preciseness. So general tolerances, here's an example of it. The part right here, maybe this dimension doesn't have to be really exact. So for this 4-inch mark, it would be plus or minus 1/100th of an inch because it's got, you know, 2 numbers showing after the decimal place, and so it would be plus or minus 100th. And same thing for that 3.0. So upper limit, and then that gives us the lower limit, and then the tolerance would be subtracting the 2, so it would actually be able to be off by up to 2/100ths of an inch between different parts. All right, so out of tolerance. A manufactured part is said to be out of tolerance if the part is not within the specified limits. Manufacturing facilities often institute quality control measures to help ensure the parts are within the tolerance. One of the ways that they do this is by making sure that their equipment is precise. So their dial calipers are actually inspected and repaired, and they do that every couple of weeks to make sure that their calipers are very precise. Now, for some companies that are doing aerospace work, it's even higher, and so you'll see that as a cost to a manufacturing company and a reason why your part, if it's very precise precision tolerancing, would need or be more expensive because that's an extra added cost for that manufacturer. All right, there's different types of fits. So a clearance fit, it limits the size of the mating parts so that the clearance is always resulted when the mating parts are assembled. That means that it has a looser fit. So there's always some sort of little gap between the pieces that are fitting together. And they want to have like a minimum spacing between there to make sure that parts maybe like slide better or something like that. An interference fit, it limits the size of the mating parts so that the interference is always resulting. So if you think of something like a shim for a door or something like that, you want it to impact and like, you know, or something that would be tapered. You want to make sure that it actually has a snug fit. So if something's like needing to be held in place or something like that, you do want them to actually like interfere and have a tight fit. A transitional fit occurs when 2 mating parts can sometimes have a clearance fit and sometimes have an interference. So the transitional, so I guess a taper would be an example of that transitional fit as well. Interference would be like, I want these 2 things to stay interlocked. So once they're fit together, they have a certain amount of friction. All right, clearance is always a clearance between the axle and the opening. So if this was a disc and then the opening. So for this one, notice that at the maximum size of this rod would be 10, and then the minimum size of the hole would be 10.15. So there's always the difference between those two. So there'd always be 0.15 inches of clearance. So a little more than 1/8 of an inch clearance in here so that this piece can easily fit in and out. Interference fit. So this hole, even at its maximum size, is 9.99, and then at its maximum or minimum size of the rod is 9.92. Now, if you try to fit them together, it's going to not work. The rod is bigger than the hole, and so it would probably result in like crushing. So think of like an axe handle or those kinds of things. You kind of like it has an interference fit where the handle won't come off of that, partially because you hit the end of the handle and make the wood expand, but it's definitely an interference hit or interference fit. Definition. So maximum material condition, so the MMC, is the condition of a part when it contains the largest amount of material. The MMC of an external feature, the length of a plate, is the upper limit of the dimensions. So an MMC matters, like think about if you were going to build something and you were buying plastic to mold those things. How much plastic do you need to buy? Well, you buy for the maximum material condition, because if all your parts are at the upper limits of those dimensions or the tolerances, you want to have enough material to actually be able to fill the mold or to be able to manufacture or cut those pieces out. Plus you need to buy a little bit more for any parts that get scrapped for error. So you want to think about that like cost-wise. If you were going to like try to estimate for a customer, how much would it be to engineer and manufacture a part? You would be able to give an estimate based on that maximum material condition. You don't want to bid it at the lowest for your tolerances. You want to bid it at that maximum so that you don't end up having to eat that cost. The least material condition is the condition when the parts contain the smallest amount of the material. So if you had it at the lower limits of the dimensions and tolerances, you wouldn't have as much plastic or metal or those kinds of things in that material, but you want to manufacture for that most, the maximum. So allowance is the maximum clearance or the maximum interference between a part. And to calculate allowance, the MMC internal feature minus the MMC external feature, and it gives you the difference. So that's kind of what we were talking about before. So maximum material condition for the hole is 10.15, and then the maximum material condition for the axle is 10, and it results in that gap. There's still a maximum material condition here as well, so between the smallest and the smallest measurements, we end up with that 0.15 allowance. So in general, the more significant figures in the dimension, the tighter the tolerance. Overly precise dimensions and overly tight tolerances increase the manufacturing cost, and specific dimensions only to the precision and tolerance necessary for the parts to function properly. So you don't really want to put too many tolerances on, but there are some of those generic ones that you can put on there that help with tolerancing. So for the assignment for tolerances, what you guys are going to do, read your introduction, kind of helps give you some explanation on things, and then what you're going to do is you're going to identify whether they are a unilateral, a bilateral, or a limit. Go down. And you're going to list them A through Z. So you're going to go through using all of those different types of dimensions. You're going to pull up the slide here. So limit, bilateral, and unilateral. You're going to pick which one it is, and you're going to specify what it is. So I've got 3 different parts in this packet, and you're going to start with label A on the adjustable rocker arm, and you're going to write down whether it's unilateral, bilateral, or limit, and you're going to write Y. You're going to specify what its tolerance is, so you're going to have to do some math there to tell us what the tolerance is. Use the slideshow to help review if you need, and you're going to tell us Y. And then you're going to put this letter, so if this was A, you're going to put it next to your part. Now there's 3 parts, like I said: adjustable rocker arm, base plate, and the drill block. So those images are down below here, and you can actually add to these lists. So like if I need more for the adjustable rocker arm, if you're in this box and hit enter, it just adds, it should add, or you can copy and paste some more lines. So like you could copy and paste these and add more lines to this. I do believe you guys are going to want to have this open in Microsoft Word, I believe, because I think it's going to do weird things if you leave it in a Google Doc. So you're going to want to download this from Google Classroom. Right, but here's my adjustable rocker arm, and so let's say that, let me go back to here, let's say that this was my first part, and I wanted to, oops, I don't know what happened there, I wanted to specify, you know, this as a bilateral tolerance. So I'm going to go to Insert, and then I use a clip or a text box, sorry. So I've got a text box tool right here, and I always click draw the box. And then what you can do is you can just draw the little box on here, and I'm going to label it A. And you can make it smaller or move it closer as you need. It might do some strange things there, but try to draw the little text box in here to label it, and see that's kind of an easy thing for you to do. If you have another way that you can get them to label next to the one that you're talking about, then that's great. So then you come up to your chart for the adjustable rocker arm. You know, tolerance type is unilateral. My explanation was between, and I'd have to write down what those dimensions are between, so 0.536 and 531. Right, and then I have to list my tolerance, so I'd have to actually like subtract those two numbers. So my tolerance is 0.005, and Y, it lists the max and minimum size. All right, so that's an example of the first one, and then I continue on to B, C, D, right? If I can't find any more on the adjustable rocker arm, you're going to go onto the base plate, right? So this is adjustable rocker arm. I see, just off the top of my head, I see 1, 2, 3 right now, and that's not including these down here. Okay, so these right here for the adjustable rocker arm also count. So you could use those as well based on this little note right here. And then go down here, this is the base plate, all right? So you can see there's some different types of tolerances. So there's at least 1, 2, 3, 4 that are right off the top, and then plus it has another specification here for so unless otherwise specified. And then again down here, this is the last part, it's called drill block. So you're just A through Z for all those, find all the different tolerances, list what they are and why they're there. You can use a lot of, once you do, you know, explanation and stuff, you can, like the Y part, you can change it up pretty easily. And then number 2, that's number 1. So problem number 2 asks you to do, still talking about a part that goes with that rocker arm. So you're going to be utilizing, if I come back up here to the rocker arm, I'm going to be utilizing this general tolerances section to help me with this rod that's down here. So it's talking about this little dimension picture here, and it says, it asks me questions about it. So it says, do you use the general tolerances from the rocker arm above, but you're also going to go through and look at like what's the tolerance for the diameter. So you're going to talk about that right here, and you can just type your answers in here. What's the tolerance of the rod length? Well, the rod length is right here, so that means I'm going to have to go back up to those general listed tolerances specifically for the rocker arm. So make sure that you scroll all the way back up. The rocker arm is the first one in the first problem, so all the way up here. And it's going to continue to ask you questions about what kind of fit it is, what's the smallest, the allowance between the rod and the smallest hole. And so it's going to ask you some specifics. So you're going to have to look at that rocker arm part, and you're going to also have to look at that rod to be able to answer those questions, and then do your conclusion questions. If you have questions, please let me know.